Hello, this is Tyson Ochsner, and I'm happy to have this opportunity to talk with you about some of our research, trying to better understand the relationships between soil moisture and wildfire danger, particularly in the context of grasslands, such as you see here in the photo. I am very much indebted to a wonderful interdisciplinary team of colleagues that I have had the privilege of working with in this line of research. Folks that you see here on the screen, as well as others coming from a wide range of different backgrounds and skill sets. And I have learned so much from them and really enjoyed working with them. Our motivating question has been to understand how increasingly available soil moisture information can be used to better manage the impacts of fire on people and ecosystems. And we've learned some great lessons along the way. And so I want to hit just some of the highlights of our journey so far and then hone in on two here at the end. First of all, we've learned how soil moisture affects growing season wildfire size in the Southern Great Plains. And that work is published in Soil Science Society of America Journal, as linked there. We've also learned how current and antecedent soil moisture conditions relate differently to wildfire in different seasons, particularly during the dormant season versus during the growing season. And that work is published in the International Journal of Wildland Fire. Furthermore, we've learned that soil moisture data, soil moisture measurements are a better growing season wildfire predictor than the Keach-Byram Drought Index, which is widely used in this context. That work published in 2017 in Soil Science Society of America Journal. More recently, we have learned and discovered how grassland fuel bed conditions are related to, are linked with the soil moisture conditions. And these results were published in the International Journal of Wildland Fire. And then finally, most recently, we've learned how soil moisture information can help improve predictions of grassland fuel loads. And this publication is forthcoming in Agronomy Journal. I want to hone in on these last two and share some of the highlights with you from those studies. These studies drew on field data that was collected at the OSU Range Research Station. You can see the location of the study site here on the map of the USA, and you can see an aerial image of the study site, giving you an idea of the relative distribution of the trees and the grasses in these areas. We worked in 3 pastures like the one shown here. They were under patch burning management and were grazed by cattle at a low stocking density. Tallgrass prairie vegetation was predominant here. The soils were very heterogeneous in these pastures. The climate is a subhumid climate, and the instrumentation included soil moisture stations distributed throughout these pastures, a complete weather station, which actually located here in the photo, and an eddy covariance tower to allow us to measure carbon and water fluxes. So right to the data, to the results here. These data illustrate how grassland fuel moisture conditions are strongly linked to soil moisture. So we have here in the left-hand column data from the 2012 growing season, and in the right-hand column we have data from the 2013 growing season. The top panels are FAW, that's pronounced FAW, or stands for fraction of available water capacity. This is our measured soil moisture, is scaled to range here from 0 to 1. And what's very clear, if you look at the data, is the declining trend in soil moisture conditions from early June 2012 up into August of 2012, reaching low levels. Once we drop below about 0.2 in this fraction of available water, we are under extreme drought conditions. The dashed line shown here is August 3rd, 2012, which is the date that marked the beginning of a major wildfire outbreak near our study site. And that wildfire outbreak burned over 34,000 hectares. And it occurred starting on August 3rd when the soil moisture levels were around 0.24, so at quite low levels. You can see here the next 3 rows of panels are the fuel moisture metrics that we measured. The first one is GFM, that stands for green fuel moisture. That's the fuel moisture of the herbaceous vegetation portions that are totally green, so not senescing at all. So those fuels, you can see the moisture was declining along with fall. Likewise, the mixed fuel moisture, this is the fuel moisture you get if you sample the entire herbaceous fuel bed together. And you can see the mixed fuel moisture likewise declining along with the soil moisture levels. And both the green fuel moisture and the mixed fuel moisture reached their minimum values right at the time of the wildfire outbreak. In 2013, it was a wetter year. We had generally higher levels of soil moisture, shown here as fall, higher levels of green fuel moisture and mixed fuel moisture throughout the year. The bottom one is the dead fuel moisture, which does not vary that much and did not show a strong association with the soil moisture conditions. In 2013, there was a rapid decline in soil moisture levels in September, which was also reflected as a rapid decline in the mixed fuel moisture in September 2013 as well. We then pulled out the data to look more directly at the relationship between soil moisture expressed as fall and the mixed fuel moisture, and also the curing rate of the fuel bed. Here are the results. We found here that there is a breakpoint in the relationship between soil moisture expressed as fall and the mixed fuel moisture. That breakpoint occurs around 0.59 on the fall scale. And when soil moisture is declining and when it drops below 0.59, we have this strong linear relationship between the soil moisture and the fuel moisture of the mix. Likewise, if that drying continues, when fall drops below a second breakpoint at 0.3, that's when we begin to see curing. That's when we're able to see measurable transfer of live fuels to dead fuels. And so the rate at which that transfer occurred was a linear function of fall once fall dropped below 0.3. So that's a very interesting result. We found that the maximum curing rate reached up to 13 grams per meter squared per day, and it occurred during that time in September 2013, which I pointed out on the previous slide. During that time, fall averaged 0.21, so exceptionally dry conditions. I want to switch now from talking about fuel moisture conditions, and I want to talk about fuel loads. So the amount of herbaceous biomass is generated in these grasslands. Now we're going to be looking at grasslands across Oklahoma, which has a substantial variation in precipitation across the state. We'll be using data from the Oklahoma Mesonet, which is an outstanding monitoring network that we have spanning the state. And we're using data from the National Agricultural Statistics Service on a variable that they call wild hay yield, which we have chosen to be representative of grassland fuel beds. To develop our model, we focused again on the Range Research Station, particularly a site called the Marina, Oklahoma in situ sensor test bed, where we had the soil moisture measurements, we had the flux tower, and we had the vegetation sampling. The model that we use here is relatively simple. The first step in the model is to estimate the evapotranspiration, shown here as ETC, and we estimate that by scaling the reference evapotranspiration according to 3 coefficients. So the reference evapotranspiration is estimated from standard weather data. This coefficient KCB, that's a basal crop coefficient, is varies with time throughout the season and is determined by a set of vegetation parameters that we need to estimate. The next 2 coefficients are related to soil moisture, and they are calculated based on a simulated water balance. So the previous day's estimate of evapotranspiration feeds back to adjust the water balance, which then adjusts these coefficients for the subsequent day. The second step in the model is then to extract the estimated transpiration, shown here as T subscript C, and to normalize that transpiration by the reference ET, as shown here. And then we calculate the cumulative total of that normalized transpiration, multiply it by a constant that's called the water productivity, and from that we get an estimate of the biomass. Now we need to calibrate this model, and we use data from the moist site. We use evapotranspiration data to help us calibrate these vegetation parameters, and we use the vegetation sampling to help us calibrate this water productivity. Then we ran the model with and without direct insertion of soil moisture data. So if we don't have soil moisture data, we run the model as shown here in the flow chart. But if we have soil moisture data, we can get rid of this loop, this simulated water balance, and just insert the soil moisture data directly to calculate these coefficients. And so we ran it both ways. Then we took the model and applied it in 25 counties across the state of Oklahoma, across 3 different years. Here's what we found. We found that the model does quite well in simulating evapotranspiration. The green here is the measured evapotranspiration from the flux tower. The black line is our model with the insertion of soil moisture data, and it performed well, but it performed about equally as well whether we included the soil moisture data or we did not include it. So the model is quite effective for simulating evapotranspiration. The values here, NSC, stands for the Nash-Sutcliffe efficiencies. We want those to be close to 1, and they were quite good in both the calibration and the validation period. Next, we need to calibrate the model for biomass. And to do that, we took our vegetation samples and plotted our accumulated above ground biomass versus the cumulative normalized transpiration, as shown here in the top panel. And the slope of that line gives a water productivity of 45 kilograms per hectare. This is a value that needs some further testing. We don't really have any similar values in the literature that we can compare this to determine if we're on the right track here, but it seems reasonable, and we find that the resulting seasonal trend in above ground biomass accumulation reasonably reflects what we observed in the field at our calibration site. So now we've calibrated the model, and we then apply it across the state in these 25 counties, and here are the results. And again, I'm just showing the results for the model with the insertion of the soil moisture data. You can see on the y-axis the measured fuel loads, and on the x-axis here the predicted fuel loads. The data follow the 1-to-1 line. We have a Nash-Sutcliffe efficiency of 0.65 and a mean absolute error of 270 kilograms per hectare. If we do not insert the soil moisture data, the predictions were not as good. Nash-Sutcliffe efficiency was only 0.10. So in conclusion, we have seen and learned how grassland fuel moisture and curing rates are both strongly linked to soil moisture, particularly as soil moisture declines below these two thresholds shown here. We've also learned how assimilation of soil moisture observations can help improve predictions of these grassland fuel loads across a relatively wide range in fuel loads. So, we look ahead to possible next steps that might include evaluating the use of soil moisture observations in the current fire danger rating systems. That data could be used to estimate the fuel loads or to estimate the fuel moisture. We also are interested to learn more about the differences and the synergies between the in situ, the modeled, and the remotely sensed soil moisture products in the context of fire danger rating systems. So again, thank you for your attention. I thank the sponsors of this work and all the people who have contributed to it over the years. And I just invite you to get in touch by email or by any of our websites, whether that's our high resolution soil moisture mapping website, our Canopeo app, which is great for monitoring vegetation conditions in the field, or just our general soil physics website where you can learn about our program. Thank you so much for your time and attention.